Okay, so let's go back and continue our dive into simple harmonic motion. So we're going to look at the dynamics of simple harmonic motion. So if we start at our maximum amplitude, we are going to have a restoring force that is pulling that object back in. In this case, we have a mass on a spring, so that force is going to be based on Hooke's law. So that force is going to be equal to negative kx. Now, that means that the force that we are experiencing, which is also equal to the mass times the acceleration. So at this point, things get a little weird. Now remember, we said that acceleration is directly proportional to that position. So what we get is that the mass times the acceleration, remember that was negative 2 pi over the period squared times our position, is going to equal negative kx. So the negatives are going to cancel. Yay. No negative gremlins here. I'm going to look at this x. Now, we're going to look at this as a non-equilibrium position, so that x is not 0, is kind of how we're going to look at this. We're going to look at this when we are away from that equilibrium position. So if I look at it from that perspective, I've got 2 pi over the period squared should equal k. So if I want to find an expression for the period, what I could do is recognize that I've got that mass, I divide it by my spring constant k. I'm going to square everything, so 4 pi squared over the period squared, that's going to equal 1. If I divide that k over and I square everything, I'm going to multiply that period squared over. So I've got m over k equals m over k times that 4 pi squared. So times pi. That's going to equal my period squared. It's a little bit messy here, but we're going to clean it up. What that's going to give me is that my period is going to be the square root of m over k times 4 pi squared, which tells me that I've got 2 pi. Yes, the square root of 4 is 2, the square root of pi squared is pi, m over k. So that is my expression for my period. So that means that the period of my oscillatory behavior does not depend on how far I pull that out. It is not, all it depends on is going to be the mass that's attached to the spring and how stiff the spring is. It does not depend on the amplitude at all. There is zero dependence on the amplitude. So, if I recognize that frequency is 1 over the period, I can connect this to frequency. So keep in mind that we have said in this case there is no external net force. So that means that there is no friction at this point in time. We have neglected friction. So if I look at this from this perspective, keep in mind at maximum amplitude we have our elastic potential energy as our maximum, 1/2 kx squared. We've said at the equilibrium position that all of our energy has converted to kinetic energy. So that means we are looking at 1/2 mv squared. So what's going to happen is if energy is conserved, that means that our potential plus kinetic at the maximum amplitude, I'm going to put A here, is going to equal our potential plus our kinetic at our equilibrium position. So maximum amplitude, I'm going to have 1/2 k a squared. This goes to 0. At our equilibrium position, this is 0, so I have 1/2 mv squared. We've already set at equilibrium, this is going to be our maximum velocity. So the 1/2 can go. So I'm going to divide by m, so I've got k over m a squared is equal to v squared. This is our maximum velocity. So our maximum velocity is going to be a times the square root of k over m. So if we have a heavy mass, we're going to have a very low velocity. If I have a large amplitude, my velocity is going to be faster. If I have a stiff spring, my velocity is going to be faster. So keep that in mind. That's where this equation is coming from. So again, we have neglected air resistance, we have neglected friction, we have said energy is conserved, we are looking with an idealized system. So this is an idealized system. In our everyday lives, you have experienced that eventually there is some resistance, whether it be air resistance, whether it be some sort of an external force that causes that motion to eventually come to rest. Otherwise, our cars would be sitting in the parking lot, bouncing after going over a speed bump for hours and hours and hours, and it would be really hard to drive them. So keep that in mind. We've neglected a few things in the sake of making the math and making the concept as streamlined and idealized as possible at this point. So this is the example we have looked at in class. So we have a body mass measurement device, a body mass measurement device chair. The chair itself has a mass of 32 kilograms. It has a vibrational period of 1.2 seconds when it's empty. We're going to put an astronaut in that chair, and we are going to let it go. So the period is going to change to 2.1 seconds. We want to determine the effective spring constant of that chair's spring, and the mass of the astronaut, as well as the maximum vibrational speed if we give it an amplitude of 10 centimeters. Okay, so first off, we want to find information about the spring constant of the chair when it's empty. So this is our part A. So the period of the chair is going to be 2 pi times the square root of m over k. We know that this was 1.2 seconds. We have 2 pi. We were given that the mass of the chair was 32. And we are going to solve for k. Now, this is one way of doing it. Another way of doing it is we could go ahead and solve everything for k and then put our values in. So we would have t over 2 pi equals the square root of m over k. Square both sides, so we would have t over 2 pi quantity squared equals m over k. So now I'm going to flip this fraction and multiply on both sides. So we're going to have m 4 pi squared over the period squared. Either way we do this, as long as we are being mathematically accurate, we should be fine. So for this, I'm going to get that my spring constant, when I put it through the random number generator, is approximately 877 newtons per meter. So that's how stiff that spring is. Now the next step is I want to find the mass of the astronaut. I'm going to use the same equation. Period is equal to 2 pi square root of m over k. I'm going to do some rearranging. So I've got the period over 2 pi equals the square root of m over k. Again, I'm going to square both sides, so t squared over 4 pi squared is going to equal m over k. So the mass is going to equal the spring constant times the period squared over 4 pi squared. Now, this mass, it's important to recognize, is going to be the mass of the chair plus the mass of the astronaut. So our spring constant times the period is, for this one, was 2.1 seconds. We're going to use the spring constant we just calculated, and if we plug all of that into our random number generator, we are going to get that the mass of the astronaut is approximately 66 kilograms. So the next thing that we wanted to know is for this problem, the maximum vibrational speed. So if I want to find the maximum vibrational speed, I can go back up to this equation, square roots of k over m times the amplitude. So the maximum vibrational speed it's important to recognize that this is going to be the mass of the chair times the mass of the plus the mass of the astronaut. So I've got 877. I've got 32 plus 66. My amplitude was 10 centimeters, so 0.1 meters. And if I plug all of that in, I'm going to get approximately 0.3 meters per second. So when we start looking at a vibrational system, not only do we have a mass on a spring, we have another option here, and that would be a pendulum. A pendulum is a vibrating system. The motion is very apparent if you've ever seen a grandfather clock, that tick-tock. So we're going to look at a very simplified version of a pendulum. There are multiple types of pendulum systems, so we're going to look at the easiest version, and that is a bob on a string. A simple, compact mass, we call him Bob, on a string. And we're going to use a physics string, so that means it is massless, idealized. And so this is a simple pendulum. So when we look at this, there are two forces that interact. We have the tension on the string, and we have the force due to gravity. That force due to gravity is our restoring force. That is what is going to be pulling our object back towards its equilibrium position. So what we're going to be looking at is what impacts the period. So here I have a table where we look at the mass, the string length, and the amplitude, and we say what has an impact on the period. Now, if you look at the table, you'll notice the period only changes when we change the length of the string. The period isn't going to change if we change the mass or if we change the angle that we move this pendulum back to. So what we have is this idea that our period is going to be connected to just the length of the string. Now, there is a gray zone we have to talk about. That restoring force. That restoring force was negative mg sine theta when we look at our free body diagram. Now, if I graph sine theta, it's going to look something like this. If I graph the line y equals x, it's going to look something like this. So I'm going to challenge you to graph this on your graphing calculator. You're going to need to be in radian mode briefly for this. And I want you to look at this, specifically look at it below pi over 6, so below 30 degrees. And what you find is that the deviation between sine theta and theta for very small angles, we're talking less than 30 degrees, there is virtually minimal difference. So we do something in physics that's called a small angle approximation. And we say that we can approximate this as just mg theta. And that is for small angles. We can't do that for 45 degrees. We can't do that for 60 degrees. But if we are close or under 30 degrees, we can do this small angle approximation. So that is an option that we have. So we can look at that. We can look at the tangential component of that restoring force. And so what we find is that the period is proportional to 2 pi times the square root of the length of the string divided by gravity. Does not depend on the mass, does not depend on the amplitude. It just depends on the length of the string.